Hello, this is question 4 from the Step 3 paper from 2022. So you may assume that all infinite sums and products in this question converge. Right, so that's a little bonus for us. Part 1, prove by induction that for all positive integers n, we've got this thing holding. So we've got sine x is 2 to the n, cosh x over 2, cosh x over 4, all right to cosh x over 2 to the n, sine x over 2 to the n. Okay, right, so proof by induction normally means lots of writing, which is always annoying. So let's get on to here. And well, I might as well do the base case. So we want to do positive integers n. So let's start with n equals 1. So let's do the old base case for n equals 1. So we're saying then we need at least this bit to be true. It's going to be 2. And then we're going to have cosh x over 2, sine x over 2. But that's just one of the identities, which quite often you'd just be able to assume that, but it doesn't take a lot, does it, to fill in the gaps on this. So I'm going to have e to the x over 2 plus e to the minus x over 2 multiplied by e to the x over 2 minus e to the minus x over 2 over 2. So cancel those 2's, and then I'm going to get an e to the x minus e to the minus x over 2, which is fine. So that's shown that the base case is okay. So now we have to go through the usual palaver of supposing something for k, supposing it works for k, and then showing that k plus 1 is exactly the same. So 2 to the k cosh x over 2 cosh x over 4 dot 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 cosh x over 2 to the k sine x over 2 to the k. So we suppose that for some integer k, and we've already got that working for k is 1, so that's okay. So now we need then the k plus 1. So 2 to the k plus 1, and then we're going to get the same thing with a bit of a twist at the end. So we're now going to have a cosh 2 to the k plus 1 there, and then we're going to have that with a 2 to the k plus 1. So I suppose I should put in somewhere, so 4k plus 1, we'd have that. And that is equal to, so that's pretty close to what we had before, but we've added in a 2, so we've got that from the previous bit. We've got our sine there. We've added in this 2 at the front, so we need that. Then we've added in this cosh term, so a cosh x over 2 to k plus 1, and then we've swapped in a new sine term. So we've got, that's our new one, and that is the old one that we've got, oh, not 2, an s. That's the one that we've got rid of. Okay, so we've got that. So we need that sine to not be equal to 0. So we can't have x being equal to 0 on this. So we need x is not equal to 0, which is not something they've told us, have they? They've told us that for the next part of this question. I notice here, I haven't actually read on for that bit, but they've told us that for there, but we can't have it here, otherwise things mess up. So we need all of this stuff to be equal to 1 from the 2 onwards, and that's the same identity, isn't it? Is that the same identity? We've got 2 lots of something with half the argument. So yeah, that is this. So let's call that 1 up here, that identity. So this is equal to, so definitely the right thing. So if I went up to this thing up here, this identity 1, divided both sides by sine, then I've got exactly that thing that I've just, this big mess here, this big fraction, that's equal to 1. So that was a result, wasn't it? So that's come out. So for using 1, Okay, so that's pretty much everything that I want on this then, isn't it? So that is the desired result. So by principle of mathematical induction, the result holds for all integers k. And since the result is true for n equals 1, then the result is true for all positive integers. Right, so the usual take up, the whole book's worth of paper doing induction, but still it's come out okay. So now we've got to deduce that for x is not equal to 0, then that thing is equal to that thing. So okay, that's more or less the same thing, isn't it? What have they done? So they've left us with all the coshes and they've taken everything else out. That's what it looks like. It does look like everything else is. So what have they done? They've divided the shine through, and then they've just divided it through and stuck a couple of x's in. So that's okay, isn't it? Yeah. So okay, so take the result and divide both sides by 2 to the n shine x over 2 to the n. So that will give, I mean, that is just it, isn't it? I mean, you can cancel these x's that we've got here. So I've got, that gives that divided by, why have they written it in such a stupid way? I mean, there must be some reason why they've written it that way, but it just seems a bewildering way to actually put these things down. They've put all these extra x's in here and there. So I don't really know why they want to put it this way. So, okay. But yeah, it's just a weird way to then have to actually put all of this into a format that looks like the weird format that they've got. So I get that is equal to cosh x over 2 cosh x over 4 ... all the way up to cosh x over 2 to the n. So we've got that, and then they've just written it in this odd sort of fashion. So that equals shine x over x times x over 2 to the n divided by shine x over 2 to the n. Right, sort of a weird way of putting it all down, but it's pulled everything together anyway, so that was fine. That was quite a long part 1 to this question, so hopefully subsequent parts will be a bit quicker. Right, so let's move on to part 2 then. I'll go for some blue here. You're given that the Maclaurin series for shine x is that thing. Use this result to show that as y tends to 0, y over shine y tends to 1. Right, so y over shine y is going to be y over, and what is this thing then? So when r is 0, I'm getting y over 1. So I'm getting y. Then I'm adding, what's that, y cubed over 3 factorial. Then I've got y to the 5 over 5 factorial and onwards. Okay, so let's get rid of a whole load of y's out of this. So that is 1 over 1 plus y squared. Oh, this has just dropped straight out, isn't it? Over y fourth, 5 factorial plus ... So that tends to 1 over 1 equals 1 as y tends to 0. Right, so that bit was fine. Now we've got to deduce that for x is not equal to 0, we've got that thing is holding. Right, okay, so this has got similarities to what we had up here, which is why it's been written in that weird way, I would imagine. So we're trying to show then that as n goes to infinity, we want this part, this second part here, to be going to 1. So as n tends to infinity, we've got x over 2 to the n divided by sine x over 2 to the n. So that is tending to 0 over sine 0, which is what we've just shown, which tends to 1 as just shown. Therefore, we've got the result that we want. Okay, so that was a quick part 2. Onwards to part 3. So let x equal natural log 2, evaluate cosh x over 2. Right, okay, never mind that sort of thing. So we're going to have, for that then, we will have, so cosh of half of natural log 2 is going to be e to the x is going to be root 2. Then we're adding on e to the minus x, which is 1 over root 2. And then we're going to be dividing by 2. So that is going to be 3 over 2 root 2. So that was fine. Show that. Now we need cosh x over 4. Okay, well, that's not going to be too much more difficult, is it? We're just going to have some fourth roots on this then, aren't we, on all of these? So let's do that over 4. So I'm going to then get a fourth root of 2. And then I'm going to have a 1 over the fourth root of 2 divided by 2. So that's going to be root 2 plus 1 over 2 lots of the fourth root of 2 is, which is what they've got. They've just written it with fractions rather than all of the roots that I've got. So, okay, that's fine. Use part 2 to show that 1 over natural log 2 is equal to all of those things. That's from using part 2. So, okay, switch back to red again. So we've still got our x then is natural log 2 because that sorts out at least part of the left-hand side. So let's get for sine of natural log 2. What am I going to get for that? I'm going to get a 2 minus a half over 2. So that's 3/4. So I've now got then, sticking it into here, I'm going to have 3/4 divided by natural log 2 is going to be cosh x over 2. So that was the 3 over 2 root 2. Then I'm going to have the next bit I just worked out. So that is the, well, let's put it in the order that they're writing it. 1 plus, what I put in these fractions in, okay. That, no, which one have I done? No, I've missed out the wrong one here, haven't I? I've done a 1, that's a 2, and then the fourth root of 2. Then we're going to have whatever the next one is. So we've got a definite pattern going on here. It's going to be, I'm just upping these powers each time, aren't I? Or, well, downing them, I suppose, as they go into fractions, but they're getting stronger roots every time I'm going through this. So that is going to be a 1 plus, it will be 2 to the quarter over 2 lots of the 8th root of 2. I'm kind of mixing my notation here and then going on. I've got some of them with fractions and some of them with root symbols, but still I can tidy that up in a moment. So I've got all of this. What am I doing now with this? I need to show that it's equal to that. Well, I can get rid of that 3/4 for starters. Yeah, that's going to get rid of that, and then that will go there to a 4, which, do I want to cancel anything with that 2? Not really, because they've written that in a weird way, haven't they? They've written that in a weird way. How am I going to end up getting what they've got? All those 2's dotted around there, so everything's got a 2 on the bottom. And then I've got all these other annoying bits and bobs. So what is the actual sequence here? Because I'm sort of close to it, and I've got a thing is this first bit doesn't even appear, does it? I've got a the numerators are starting in this term. So I've got this bit at the start, which just seems to be a little bit separate to everything else. I've got a 2 over root 2, which I've just sort of got stuck there at the start. So I've got this multiple of root 2, I'm not really too sure what to do with. But let's look at maybe some of the other bits then. It's the denominators that I want to clear up. So on the denominators, I've got a 1 over, I've got 2 over root 2, I've got a, but all I want to take out of these is these root bits, because all the rest of it looks great. So I've got a, I suppose I could keep that root 2 there. So I want to multiply all of these things together. I've got a 2 to the half multiply, well, minus a half actually, isn't I? 2 to the minus a half times 2 to the minus a quarter times 2 to the minus an eighth. So I need to get all of those together. So that is equal to 1 over 2 to the half plus a quarter plus an eighth. All right, so that's going to end up going to a half, because that's the frog jump into the wall thing, isn't it? If you keep going halfway to the wall all the time, then you end up getting to the wall. So adding up that sequence of a half plus a quarter plus an eighth, etc., just takes us to 1. So that ends up being a half. Okay, so all right, so that's going to cancel with the 4 in that first 2. Right, okay, so I need to actually express that in some way. So 4 over 2 times 1 over root 2 times the 4th root of 2 times the 8th root of 2, etc. Just make sure I've got all of that right. So that is 4 over 2 times a half. Yeah, that's exactly what I want out of all of this, isn't it? Which is equal to 1. Okay, so that leaving 1 over natural log 2. That first term's now disappeared. I've got 1 plus 2 to the half over 2 times 1 plus 2 to the quarter over 2 times 1 plus 2 to the eighth over 2, etc. Right, okay. So that was fiddly, but reasonable, I think. So that's done part 3. Right, so on to the final part 4. Another blank sheet up. This has been a writing intensive question, this one. So part 4, we need to show that 2 over pi is equal to root 2 over 2 times root of 2 plus root 2 over 2 plus, okay, right, this looks messy. Which one am I going to go off on this then? This one doesn't look like it's helping this thing that I've just discovered here. This looks more like it. That's got more similarities, isn't it? So how am I going to get? Well, let's assume I'm looking at this one because it does look closer. How am I going to get anything related to that? So cosh x over 2 to be root 2 over 2. Right, so we could exploit the relationship between cosh and cos. That's a possibility in this. So say we were going down that line, saying because cosh of ix is cos x. So that could be the result that we're wanting to use, maybe, in order to go from one to the other. So if I was going to make that switch, and I'm wanting a root 2 over 2 here for a cosh x over 2. So let's say I wanted cosh x over 2 to be equal to root 2 over 2. So that would be cos of pi by 4. So if I wanted that, then I'm going to need x to be equal to I pi over 2 in order to get that result. So, well, I'll quickly be able to find out then as to whether I get the left-hand side. If that makes 2 over pi, then I'm good to go on this. I'm definitely going the right way. So sine of I pi over 2 divided by I pi over 2. So for shine, that is going to be I sine of pi over 2. So that is just going to be I. Yeah, so that is I over I pi over 2, which is the i's cancel and I get 2 over pi. Excellent. Right, so I've got the left-hand side, and now I've got the first bit of the right-hand side, so I need to show then that, yeah, that cosh of x over 4 is then going to be, so I need cos of pi over 8 is what I'm going to need on this. So at the moment then I'm saying that, okay, so using x equals I pi over 2, I've now got that 2 over pi is equal to root 2 over 2 times cos of pi over 8 times cos of pi over 16, etc. So now I need to show what cos of pi over 8 is. So I'm saying then that cos, so I'm going to use my double angle then. So cos of 2, let's put this in inverted commas. So cos of 2 theta, that's cos squared theta minus sine squared theta, which is equal to 2 cos squared theta minus 1. Okay, so that means then if I want to get my cos of pi over 8, that is going to be equal to cos of pi over 4 plus 1 all divided by 2 and then square rooted. So, okay, that's kind of messy, isn't it? So that is then equal to, so root 2 over 2. So I've got a root 2 over 2. So root 2 plus 2 over 4 all square rooted. Okay, so that's come out exactly what I wanted. So I've got a 2, which way round? Yeah, I've written it that way round. 2 plus root 2 all square rooted over 2. So then I'm going to get the same thing then for, and so on, for cos the pi over 16. Do I need to show that as well, maybe? I mean, it's the same thing, isn't it? I mean, you can see we're just going to go through the same steps. And therefore, cos pi over 16 is going to be equal to the square root of 2 plus the square root of 2 plus the square root of 2, over 2, etc. So, and then, you know, result shown. That then gives that. Okay, so that followed on quite nicely as well. That was a pretty heavy question, but, you know, it wasn't, it could have been a lot worse. I mean, it looked on the page, this one, when I first saw it, I was thinking, I don't really fancy this. It didn't look as though it was going to be much fun, but it wasn't as bad as it maybe initially looked. But there was quite a lot. I normally get put off by the ones when they start doing proved by induction, because they just end up being a bit of a slog. They're not really that much fun, at least for me. But this one wasn't too bad, providing you don't mind writing out all of this stuff. And they led us through it nicely in parts 2, 3, and 4. So it was step by step. There was maybe a little bit more hand holding in this than some of the other questions, because it was, you know, some of it was quite tricky otherwise. So yeah, maybe not for me the most exciting of questions, but it's worked out okay, I think. So, you know, show that's always nice as well, because you don't have to worry about, you know, whether you've actually got the right result or not. You've got sort of marking your own work as you go along.